Swayam Prabha. Digital India. Educated India.
Welcome back to Mechanics and Control of Robotic Manipulator. So this particular class would be really going to be useful. I'm really happy to say that, because we are going to talk about one of the important concept called Danawit-Artenberg representation. So mainly we start with the kinematic parameters now. So we have seen in the last lecture like what is compound rotations. In that, two of the compound rotation representations we have seen, right, commonly used. And then we have raised the question how we can actually like get these compound rotations in a simplified manner, and how we can actually like you can say transform, or how we can actually like give the information from the specifically the orientational information from one frame to another frame in a very easiest way. So for that actually like what we have come up, so there are several attempts made. So we are going to see one simple attempt called Danawit-Artenberg approach. So before going to see that, we will see like why we are going that and how we are actually like attempting. So in the sense, we would be introducing why the Danawit-Artenberg approach and what is Danawit-Artenberg approach and what are the parameters they have used. So they simply call Danawit-Artenberg parameters. So how this all came into a picture. So that is what we are trying to see here. So if that is the case, so first thing, when you are actually like trying to give a information between two body, for example, this is one body and this is another body. So what is the easiest way? So you have to fix the coordinate. So now if you are actually like locating the coordinate, the choice of coordinate is actually like infinite, right? And location of them are also like infinite. So one of the easiest thing, we have used the Cartesian coordinate system. So that is okay, but location of them is actually like still quite open. So one of the easiest way people always do in rigid body, so they take the centroid and the centroid they will fix the frame, okay, but that may not be useful for the manipulator or the mechanisms. Why? That we will be seeing. So that is what I say, the number of parameter to describe the information between two frame is not so easy if you are actually like represent with the centroid. It is probably easy if you are talking about only multi-body dynamics in a rigid body approach, but in the manipulator approach it may not be that quite easy, okay. So that is what we are actually like trying to say. So in that sense, use of constraints and their location would be benefit rather than using centroid. For example, now I assume that these are the two body and these two body is actually like having one rotary joint, and instead of using these two CGs, can I use one frame here, okay, another frame here, okay. Similarly, I can actually like go across, so how n number of bodies. So I can actually like use these constraints, which is nothing but the joints and their locations. For example, now the joint is actually like having only vertical rotation. So in that sense, I can keep z axis here, so that I can relate the rotation with respect to that axis, rather than having a normal way of representing with respect to CG. I can actually like modify it. For example, now there is another link which is actually like rotate with respect to this in this form. So now I can keep the coordinate in such a way that I can write this form. So if that is the case, very detail I just show. So this is one body, okay. So and this is another body. So this two bodies actually like rotating. So now instead of having this, I can actually like make it my z like this, x like this, y like this. But if I do the centroid, so centroid would be coming and the centroid would be along this like, right. So instead of that, I can use that, you can say, joint or constraint and their location for, you can say, transferring the information between one body to another body. So this is one of the important aspect. So once you do this, what benefit you will get it? So there are several benefit. So before going to see the benefit, we will start. So if you have n degree of freedom spatial linkage, okay. So in the sense n degree of actually like mobility I can write. So mobility you have n number. So how many actually like bodies involved? So obviously n bodies would be involved. So in inbuilt. So what you can see, like this is actually like number of bodies. Okay. So now how many frames required? So one body each. Okay. In addition to that, you need to actually like fix the inertial frame. So in the sense you need one additional frame, and similarly you are going to use as a useful outcome on the end, so end effector frame. So in the sense if you have n axis spatial robot, serial robot, so then you have n plus 2 frames are required, so which includes base and end effector. So in that sense, how many informations you have to derive? So you have to actually like derive 6 into n plus 2, right? Can I reduce it? That is the biggest question. That is what we are actually like trying to say. So therefore, if we use a classical spatial mechanics principle, we need 6 times of n plus 2 parameters. So to describe the complete system and its overall arrangement. Okay. So if that is the case, what additional complexity will come? So there is no straightforward technique to mention the orientation of each frame. So if that is the case, can we bring it some simplified method? So there are several methods. In that, one of the popular method we are going to take. So that as given by, you can say, Danavit and Hartenberg jointly written a paper, you can say, on the kinematic parameters. So this published in 1955 in order to standardize the coordinate frame for a spatial linkage. Okay. So that is what the whole idea. It is not intended to do the, you can say, serial manipulator or serial robot. It is mainly intended to a spatial linkages. In fact, it was actually like designed for an open chain. So that is what we are going to use. So how or what they did, that we have to see. So what they said, so they said we can use only 4 kinematic parameter. So they use a kinematic parameter only 4 instead of 6. Okay. But what they said, it would be associated with a particular convention, so that you can actually like use only 4 parameter, that is sufficient to represent instead of 6. So then there is supposed to be some, you can say, pseudo or passiveness, right. So that is what we are going to see in the next slide. So but before that, what are the parameters they said? So they said there are actually like 4 parameters, but these 4 parameters would be associated with what you call link and joint. So they said, so 2 each on link and joint can be associated, in the sense the relative information of links can be represented from joint, and relative information of joint can be represented with a link. So in that sense, it is actually like somewhat tricky, right. So something is missing. So for that, what we are actually like bringing it, so the original idea what they have given in a detailed manner. Okay. So what they have given, so they said there are 2 sets. The first set would be you can say joint information, the second set would be the link information. But how they did? So they did not do anything beyond us. So what they said, we would be using a right hand rule, the first thing. So in the sense x, y and z axis would be coming as per your right hand. Okay. So in the sense if you have 2 axes, so one axis would be easily fixed based on the right hand. So similarly the rotation direction, again right hand rule, the thumb finger would be associated with your positive direction of axis. So then the rotation direction positive would be how the remaining 4 finger coming outward. This is very straightforward. In addition to that, what they said, so any link you take, that link would be having only 2 joints. So which we mean to say it's a binary links. So binary link means the link would be having only 2 connections. So any body you take, that would be having only 2 connections. Okay. So in that sense, the ground would be excluded, because the first link you take, that would be attached with the ground based on this. So then the second link to third link to fourth link, like that, keep going with the 2 joints. So because of that, what happened? So one link to another link is constrained with only 1 joint. Further, what they constrain, this 1 joint would be having provide or it allow only 1 motion. In the sense, this can actually like rotate with respect to this axis or translate with respect to this axis. In the sense, so Danavit Hartenberg indirectly they said you use binary link and each joint would be 1D of joints. Okay. So these are the constraints which they put it. So if I actually like put that way, So the kinematic arrangement, what they said, it contains only binary links. Okay. The second point, they said each constraint or joint has only 1 degree of freedom. In that sense, the joint can be either rotary or prismative, or you can call translation joint. Okay. So this is the way. Then you can ask, if I have a spherical joint, then you have to actually like virtually take 3 bodies. Okay, because it is actually like spherical joint has a 3 degree of freedom, then you have to take it's a virtually 3 bodies with 3 joints. So then only it would be fulfilled. Okay. So this handicap is there, but this is the I call pseudoness. But what we have got, so 1 D of freedom joins all the joints. So further what they have done, as I already mentioned, they have used right hand rule. So in that sense, if you have 2 axes, you can always take the third axis. Further they said 4 kinematic parameter. So they said 2 associated with link, 2 associated with joints. So for example, now as per your like as per their conditions, so this is link k and this is link k plus 1. So this would be k to k plus 1 frame, this is k plus 2 frame, like that the joint. So this is the one joint. So if I take this joint is giving what? The relative information between link k and k plus 1, right? And based on the constraint, it is only 1 D of system, the information would be actually like having only 2 forms. Okay. So what that would be? One would be angle, okay, the other one is distance. Okay. So that is what they said. So in the sense what they said, so the link parameter again, so you take, this is actually like you call one link, this link would be having 2 joints. So if I take this link would be giving a relative information between one joint to another joint. So that is what we are actually like trying to say. So in the other way around, you can say the link parameter giving information between 2 consecutive joints, whereas the joint parameter is giving information between 2 consecutive links, right? You are clear on this. So first thing, it is a binary link. So if you take any link, that would be having 2 joints, so the joint information can be given as link parameter. If you take any joint that is 1 D of system, then that would be having 2 consecutive link information, right? So we will see in detail. So in that sense, what we can see, only 2 axes are sufficient to represent this what you call Danawit-Artenberg. But what they have done, you can see like there are several bodies associated, right? So I am actually like saying this is body 0 to body n. So how I have accumulated? I accumulated one by one, in the sense I am stacking it, right? So what axis in general it is stacking? It is stacked in a z axis. So in the sense one body attached with another body is joined. So now I associated the joint associated with the joints all with z axis, in the sense z axis associated with the joint axis. So then you can see one axis associated with the joint will give one link to another link information. In addition to that, what you can see, this link is actually like expanding laterally, right? So in the sense you can see expand left to right. So what we usually write it in that way. So there is a 2 option, but what we usually say, this we would be write x, right? So in the sense the link information we will express in x axis, although we have choice of x and y, but we take x or the Danawit-Artenberg given as x. So in the sense the link information always represented with x and the joint information always represented with z. So that is what we have actually like represented here. So the joint parameter is actually like relative position and orientation of 2 successive links can be specified by 2 joint parameters. So that we will be seeing explicitly in the next coming slides. Then the link parameter is actually like the relative position and orientation of 2 successive joints. Okay. So now you can see this is the 3, you can say the top view. So this is one link and this is another link. So the joint is actually like giving what? So this giving, and the frame to frame the distance also it is giving, right? So that how I can see in the top view I can see. So this is this actually like I call the distance and this I call the orientation. Okay. So this is what we call the joint parameters which is giving, whereas you can see like the link. So I am saying that this is one of the link. So the another link is connecting like this. So the previous link is connecting. So if I take this, so this is one axis and this is another axis. So these two are having angular information and as well as the positional information. So that is what we call link parameter, which actually like giving two successive joins, right. So we'll actually like go to in deep. I said further information of this. So what said that the joint parameter always referred with z axis, because the joint information is giving with respect to the body propagation. This is one body attached with another body like this. This is actually like propagated in the vertical axis. We always take the vertical axis z axis. So that's why the joint parameter always related with z axis. Okay. So in that sense, what would be the other side? The link parameter should be represented either y or x. So x would be the best, because your link would be actually like connecting two joints that would be expand in, you can say, one direction. So in the sense, what you can see, left to right or right to left, whatever way you consider, but that we can write it in x axis, that is easier, right. So that is what the idea. Okay. So now this is actually like a link parameter. Now we will actually like see further. So in that sense, what we can actually like take it further on, the x I minus 1 axis always intersect z I minus 1 and z I. If it is not intersecting, then it should be perpendicular to z I minus 1 to z I. Okay. So in the sense, the frames are not necessarily on the link. For example, so this is the link and here one joint and this is another joint. So now you can actually like see that although it is actually like this, so even I can actually like see, so I actually like take it, this is the, you can say, link. So now this is actually like attached with another link. So you can see like even the frame can be fixed here rather than here. Okay. So like that we can actually say that say that the frame need not to be necessarily on the link, even it can be outside. Okay. So that is what the whole idea here. So let us actually like move further. So because of these all constraint, all you can say simplification, what you can see like we can use 4 parameters, that is enough to describe the frame to frame instead of 6. But what we did already, we have actually like make it a handicap or the passiveness, in the sense the y axis information we completely ignored, because y axis also would be having one rotation and one positional information that we have actually like ignored by considering that the link is binary and the joint is 1D of system. Okay. So let us actually like move to the original case, how we can actually like realize. So for example, I am taking a link k minus 1. So the link k minus 1 is having joint I minus 1 and joint I. Okay. So as per our understanding, this would be having, you can say, one joint axis which is I minus 1 axis, and this would be having ith axis. Okay. So now these two axes are actually like there, and as per our convention, the joint axis supposed to be associated with what you call z axis. So this is zi and this is zi minus 1. So now what we are actually like interested, we are interested to find how these two joints are actually like orient and distance apart. In the sense, we are trying to find out the positional information and orientational information. Okay. So in order to get that, so what we can do, we can actually like take the previous slide information, what it says. So the xi always intersect or perpendicular. So in this case, so you can see that this zi and zi minus 1 making a plane this, right. So now the intersection is not directly happen, but you can draw the perpendicular line. So that would be go either inside or outside. For betterment, because the link is propagating this side, so I am taking xi minus 1 here. So in the sense, xi minus 1 here. Okay. So even if it is not the way, so you draw the common normal between these two axes and you fix the xi axis that way. Okay. So now you draw the common normal, okay, and fix your xi axis in the propagation side where I minus 1 to I. So now what you will get, so you get one axis. Now with respect to this, you rotate zi minus 1 with some angle. So that make parallel to zi, and you translate along xi minus 1, you will reach from this point to this point, right. So now these are the two information. So what that means, So you have actually like this is 1, okay. So you can see like one of my finger is actually like coming towards you and another finger is actually like coming vertically up. So these are the two, you can say, joint axes. So when these two would be parallel, you twist this. So in other way around, it is like this, it is actually twisted like this. So now this is actually like what you can call the link twist or twist angle, right. So it is actually like the link is actually like twisted in this form. So that is what you can see. If I actually like untwist, so what happened, this would be parallel, right. So that is the first information which we call twist angle, okay. The twist angle is actually like with respect to xi minus 1, what angle? The angle between zi minus 1 to zi, okay. So that is what we can actually like write it. So now the same way what would be there? So there would be a distance, so that you can call length. So this is actually like corresponding to the link, so it's a link length. So along, you can say xi minus 1. So what the distance between this point to this point? So that is what the link length. So by nature itself, link length cannot be negative. So you always put xi minus 1 in the propagated side, okay. So that is the idea. So I'll actually like explain that even with some kind of PVC pipe in the next lecture, but let us actually like see what exactly the definition. So one is link twist angle, which we write as a alpha. So it is with respect to I minus 1 frame. So it is actually like alpha I minus 1 because we are taking rotation about xi minus 1. That's why we have written as alpha I minus 1. So what that? So this is actually like angle between zi minus 1 to zi with respect to xi minus 1 frame or xi minus 1 axis, okay. So measured about xi minus 1. You are clear, I hope. So now next thing is link length. So it is a distance between, you can say, the point which is actually like intersect, or you can say I minus 1 frame to I frame, I can write. So this is the distance along xi minus 1. So that is what you call link length, okay. You can actually like see. So the distance between zi minus 1 and zi measured along, you can say xi minus 1, you call link length. Now as per our understanding, link length cannot be negative, so that be clear. And further, as per our understanding, so the joint axis always associated with the zi or z. So in that sense, these two parameters are constant, okay. So in the sense, these two are fixed. So these two parameters are fixed, or simply you can call these are geometric, okay. So let us move the next one, we call joint parameter. For that I am taking joint I, which is connecting link ki minus 1 and link k. So now you can see like this is your I minus 1 frame xi, and this is actually like ith x, right. So this is xi and xi minus 1. So you can see like this is the joint axis, we fix it zi. So with respect to zi, you can see that there is one angle and one distance, right. So what this is giving? So link k minus 1 to ki, so link I minus 1 to link I, there is a position and you can say orientational difference. So that is what we are trying to give. So first you will actually like rotate about zi, try to make it parallel xi minus 1 to xi. So this angle called joint angle, okay. So this can be variable if you are taking a rotary joint. If you are taking zi, or you can say this to this have a distance, if you are using a translation joint, so this would be as a piston cylinder kind of thing, this would be a variable, okay. So for example, you have, this is the case, okay, this is you assume as a rotary motor you attach. So now what happened, this offset distance would be a constant, but there is offset distance, but this theta would be variable, okay. So the other case where you can see like this is you can say expanding as translation joint. So in this sense, what you can see, this distance is variable, but if you look at in the top view, if you are having some kind of angular information, so this would be constant for you because it is going to translate only up and down. So that is what we are actually like trying to say, but here what we are referring everything with respect to zi. So in the sense, joint parameter 1 is joint angle. Just joint angle is nothing but the angle between xi minus 1 to xi measured about zi, so which is actually like given here, okay. So the second one is actually like a joint distance, so which is actually like again the distance between you can say xi minus 1 to xi measured along zi. So now these two are actually like important. So in that, as per Danavitt-Attenberg, one of them is variable, okay, and sometimes the joint distance people call offset distance because it is offsetting the planes, right. So that's why it is called offset distance. So further, what you can actually like see that these two are actually like any one is variable. If it is a rotary joint, so the joint angle is variable. If it is a prismatic joint, the joint distance is variable, okay. So that is what we have given. I hope now you are clear what Danavitt-Attenberg has done. So he has given only 4 parameter which we call link twist, link length, joint angle and joint distance. We will see a little more explanation with respect to, you can say, a small PVC connection as a manipulator. I will explain on, you can say, screen. So with that we will actually like conclude the Danavitt-Attenberg parameters, and then we will go to the Danavitt-Attenberg representation, how to bring, you can say, the frame information in terms of a arm or transformation matrix. So that would be seeing in the next lecture. So until then, thank you and see you. Bye. Take care.